I think we're oh, we're not. Okay. All right. People on Discord, can you tell me whether you can hear me? Because, or rather, whether you can see me? Because I'm not convinced that you can. Hello. Is that everyone, or like the other lecture was much more full? All right. Okay. Lots of people are coming in. So the agenda for today is we're going to finish up the example that we were doing last time with primality checking, and we will then talk a little bit about project 1 and how to get started with project 1. So if you remember, just a quick review of what we've done last time. So we had a mechanism for setting I to be 0, 1, 2, and so on. So this is 0, 1, 2, and so on. And that's n1 and n minus 1. And the way we did it is for I in range n. And then you can do whatever you want with I. And I initially is going to be 0, then 1, then 2, and so on, and it's going to go up to, but not including n. And then we had this idea with using the mod. So we said that n1 mod n2 is equal to 0 if n1 is divisible by n2. Right? So if you remember, this is the remainder. So for example, 12 is divisible by 3. So 12 mod 3 is 0. Right? Because if you divide 12 by 3, you get 4. The remainder is 0. That's because 12 is divisible by 3. So on the other hand, you do 12 divided by, 12 divided by, let's say, 5. Well, that would so that's just 0 with a remainder of 5 actually, so not equal to 5, right? Sorry. So in general, if it's equal, then it's divisible by the second number. If it's not equal, then it's not divisible by that number. Yeah. Yeah, it should. Yeah, it's 2. Sorry. So that's because 12 divided by 5. So 12 divided by 5 is 2. So 2 times 5 is 10, and then the remainder is 2. Sorry. Yeah, it's on YouTube now. Oh well. Okay. So that's like that. So we can combine those two ideas in order to test whether a number is prime or not, right? So, for example, we can look at a number like 81. Well, that's not prime, that's 3 cubed. How do you check whether it's prime or not? Well, you can say, I'll see if n mod 2 is equal to 0. And then I'll see if n mod 3 is equal to 0. And so on. And then I'll see if n mod n minus 1 is equal to 0. And if one of those is equal to 0, that means that you found a divisor. So n is divisible by one of those numbers. On the other hand, if you check all of those and none of those are equal to 0, then that means that the number must be prime because, well, you tried every possible divisor, it didn't divide n, so n doesn't have any divisors other than itself, so that means that it's prime. Make sense? So in this case, well, that's no, but that's yes. So 81 is divisible by 3, so 81 is not prime. On the other hand, a number like 83, well, it will turn out that it is prime, unless I'm messing up again. It is prime. Right? So you try 2, 3, 4, 5, that nothing divides it because it's prime. All right? So now what I want to do is just put it in code. So I'll write my function, so that's going to be is prime. And what I'm going to do is I'll start with something that's slightly wrong. So I'll say for I in range n, and then I'll say if n mod I is equal to 0, I'll return false. And over here, I'll return true. So this is basically the idea, right? So try n mod everything, but it's not quite right. So the reason it's not quite right is like here I'm saying for I in range n. So that means that I is going to be 0 and then 1, then 2, then 3. You can't even do 12 mod 0 because this is saying if you divide 12 by 0, what would be the remainder? The answer would be, well, nothing, because you can't divide 12 by 0. So you'll just get an error. So here I'm saying for I in range n, so I is 0, 1, 2. So a trick you can use is you can say, well, and that's not the only solution, but you can say, well, instead of saying n mod I, I'll say n mod I plus 2. So now if I is, let's say n is equal to 5, so if I is 0, 1, 2, 3, 4, then that means that I plus 2 is 2, 3, 4, 5, 6. Right? So here, if I'm saying n equals 5, so what would I try? I would try n mod 2, 3, 4, 5, 6. So progress, I'm not trying 0, but of course, if n equals 5 and I try 5 mod 5, that would be 0. Always, like a number divided by itself is always 1 with the remainder of 0. So you don't want to check 5 mod 5, you want to check up to 5 mod 4. So how do you do it? Well, this is for range n, and this is for range n. Well, I can just say, okay, so I'll do range n minus 2. So that would go, I would go up to, but not including n minus 2, so up to n minus 3. In this case, if n is 5, up to 2. Up to, yes. So if I goes up to 2, that means that I plus 2 goes up to 4. So I plus 2 would be 2 and 3 and 4, but 5 and 6 are not included. Why? Well, like here I just have a concrete example. So if I'm saying I in range 3, then I goes 0, 1, 2. So I plus 2 goes 2, 3, 4. So I'll write that explicitly as well. And then you add 2, you get 2, 3, 4. So that means that over here, if I say for I in range n minus 2, this would do it, right? Because I'm going, in this example with n equals 5, I'm going try dividing by 2, try dividing by 3, try dividing by 4. And that's what I want. There's more efficient way, there's kind of more efficiency to be gained here, but that about gets you to what you need. Right? So I demonstrate, so probably if you kind of are more experienced, you would probably not write things out this way. However, like, I'm sure that if many of you look at this code, like it's new, and like, of course it's confusing, like there's a -2 there and a +2 there, so it's inherently confusing. So writing things out like that with a concrete example always helps a lot. So just always do it. If it seems like you're confused, like should it be +1, should it be -1, just write it down and see what happens with a concrete example. Of course, like, it's possible in principle that your concrete example is not representative and that the thing wouldn't work with another example. That could happen. Well, the answer to that is to try more examples, is not to not try any examples. It's like always useful to plug in a concrete example. It's always useful with respect to like figuring out, like, should it be exactly +2, whatever. All right. So, okay, let's check the Discord. Oh my God. All right, Discord, are we doing okay? I think it should work. So, okay. So, yeah, I'll maybe switch to some other software. This seems unreliable. So this is the code. So we can now say, okay, all right, I'll just try to run it. And first I'll just try whatever is prime 5. So here 5 is prime, so 6 is not prime, so that's good. So let's see how it runs for is prime 5. So I'll put a breakpoint here, and I'll step in. So here I'll check, okay, n is 5. So it says for I in range 3. So I can check that n minus 2 is 3. So we're stepping in, and we're saying if n mod I plus 2, so I plus 2 is 2, 5 mod 2 is 3, no, 1, sorry. So that's not equal to 0, so that means that we're not returning false. So we're trying the next I. So now I is 1, I plus 2 is 3, so 5 mod 3 is 2. So because 5 divided by 3 is 1, so to make it up to 5, you need 3 times 1 plus 2. So that's again not equal to 0. So what happened here is I was 0 and then 1 and then 2. We said for I in range 3, so we go up to but not including 3. We never got to return false because it never was the case that n mod I plus 2 was 0. So finally we got to line 28. so we're returning true. 5 is prime, so that makes sense. So in general, what's the logical structure here? So the logical structure is you're saying for every possibility of a divisor, for every I plus 2 that makes sense, check if it's really a divisor. And if it is, the answer is false. The answer is n is not prime. If you tried every possible divisor and didn't return false because it wasn't an actual divisor, then after the for loop, you get to the return true. Right? So the logical structure is return false if any of the I plus 2's checks out, and return true after checking every possible I plus 2 when it turned out that none of them checked out. So a common incorrect thing to do is to write else return true here. So the logical structure here would not make sense for the problem, because here you're saying if it's equal to 0, return false, else return true right away. So what would happen is if the number is not even, you would try if n mod 2 equal to 0, that's not true, and then you get to return true right away. But of course, just because the number isn't divisible by 2 doesn't mean that it's prime. You need to check all the other possible divisors. So, and this just says like, if it's equal to 0 right away for the first I plus 2, if it's equal to 0, return false, else return true right away. Not what makes sense. You need to check every possible divisor. So this is kind of a common incorrect thing. This is different because the return true is outside the for loop. So the for loop runs, and if you hit return false, well, that's because you found a divisor. If you never hit the return false, then eventually you'll get to the return true. All right. Now, of course, there's different logical structures. It depends on the problem what you need to do. It's very rare that you would have this kind of thing, because this kind of thing, well, it doesn't matter what I is. You'll either return false right away or return true right away, because it says like either return false or return true. And sometimes that's what you need, but if that's what you need, then why would you need a loop? So inside the loop, this would never make sense. Is that making sense? Questions? Yeah.
Can you explain again why you can't put else return true?
So you can, it just doesn't make sense in the logic of this particular problem, right? And indeed, any other problem inside the loop, it wouldn't make sense, right? And that's because what does it mean to say if whatever return false, else return true? Well, it means check this condition. So Control T is uncomment. I don't usually use it. So check this condition, and if the condition is true, so if n mod I plus 2 is true, is equal to 0, then return false. And then you say else return true. So it's going to be for I equals 0, you'll check, and if the equality holds, you return true. If it doesn't hold, then you return false. You might imagine that for some problem, that logic would make sense. But not for this one, because when you're checking for primality, just because n mod 0 plus 2 is equal to 0 doesn't mean that the answer is true. The answer might still be false.
So then, does that mean if you put else return true, that it doesn't check all the other i's?
That's right, because if you say return true, like if you get to return true, it returns true. Like that's what it means to say return true. Yeah.
So in a function, after you, like when a return statement
Is
run,
reached.
and does it skip the rest of everything?
That's right. Well, you can't both return true and false. It's got to be one or the other, right? So that means that once you get to a return, that's it. All right? Questions? All right. So that's like that. So one thing that you might worry about is, oh, like we always checked, is it divisible by 2, is it divisible by 3, is it divisible by 4? So what about 2? Because 2 is a weird kind of prime number. It's even, but it's prime, right? So is it a problem? Well, in this case, 2 specifically is not a problem, because if you say for I in range 0, that means that you go from 0 up to 0, not including 0, so that's just nothing. So that means that this would just never check anything, because like if you say for I in range 0, it doesn't print, because it's 0 up to 0, not including 0, is just nothing. So that is what would happen here, is you would say for I in range 0, and there's no i's in range 0, so that's fine. Now, another thing that you might wonder about is, well, like what about 0 and 1? So for 0 and 1, you would actually not do this, and you would also return true, even though 0 and 1 are not usually considered prime numbers. So you might say something like if n is more equal than 1, then just return true, false, whatever. Now, this includes negatives. It also includes things like minus 2 times pi or whatever. In Python, you cannot worry too much about those things, because you can't police what the user will give you, right? So you can't say, oh, you're not allowed. I mean, you can, but it's usually not done. So usually you don't say, oh, like I'll check whether you sent me a float, and if it's a float, that doesn't count. Or like if you sent me a string, it definitely doesn't count. In Python, we just usually don't worry about it. It's up to the user to provide valid input. Now, in this case, you could argue, well, like 0 and 1 are valid inputs. It's valid to ask whether they're prime or not. Minus 2 times pi plus e is not something that's valid to ask about, so not worrying about it. In principle, you could do something more robust if you wanted to. That would probably involve not just writing a function, but interacting with the user and like asking them for input and making sure that the input makes sense, stuff like this. So not really concerned about it when just writing a function where we assume that the user is behaving themselves and is sending something that makes sense. All right. Questions about this stuff? Yeah.
From your like separate like analysis, like when you wrote this, you first analyzed significant n that is significant large enough, then you analyze special cases of 0, 1, and 2. Does this mean when we are writing for a number?
Okay. OBS is really